All right, in this video, we're looking at relative extrema and critical numbers. So in this figure 3.2, you can see that the graph of x cubed minus 3x squared has what's called a relative maximum at the point 0, 0, and a relative minimum at the point 2, negative 4. So informally, for a continuous function, we're really thinking of relative maxima occurring at a hill or a peak of a graph, and a relative minimum is occurring at a valley of the graph. So anywhere that one point is higher than every point around it, right? If it goes down on both sides, that's a relative maximum. Same with the relative minimum. If everything around it goes up, then that means it is the lowest point in that area. So these hills and valleys can occur in two different ways, okay? Either smooth and rounded or sharp and peaked. Now, if it's smooth and rounded, then we know that the graph has a horizontal tangent line at the high point, right? If it looks like this, we know it has a horizontal tangent line. We were going to pretend those touch. A horizontal tangent line at the peak, right? Now, if the hill or valley has it sharp like that, then we know that it's not differentiable because of one of the definitions of differentiability. So either at a relative extrema, either one of two things is going to happen. Either we're going to have horizontal tangent or non-differentiable, okay? So here's what we're going to do. We're going to define very clearly. There's an open interval containing C where f of C is a maximum, then it's the relative maximum of f. Let me say this again. If there's an open interval containing C on which f of C is a maximum, then we call it a relative maximum of f, okay? Excuse me. Or you can say that the relative maximum of f is f of C. So f of C is the actual value. C is where it's located at. Now, if there's an open interval containing C where f of C is a minimum, then it's called a relative minimum, or you can say that it has a relative minimum at C of value of f of C. Now, you may have heard me say this, but the plural of maximum is maxima. The plural of minimum is minima. And sometimes we refer to these relative maxes and mins as local maximum and minimum, okay? So let's look at a couple of things. We want to look here and say, what is the value of the derivative of each of these functions? Well, here's the relative maximum. This is at a curve, right? So we know that it has a horizontal tangency. But the horizontal tangent line means that it has a slope of 0. But the slope of the tangent line is the derivative. So the derivative equals 0. So right away we know that the derivative is 0 anywhere where there's a relative maximum or relative minimum that is at a gentle curved peak or valley. Now, if we have a sharp peak here, we know that it's non-differentiable, right? Because there's an infinite number of possible tangent lines. So this is non-differentiable. So there is no derivative. Over here, once again, horizontal tangent line, horizontal tangent line. Both of these have a value f prime pi over 2 equals 0. F prime of 3 pi over 2 is also 0. Okay, this over here I should have said f prime of 3 because that's the value at x equals 3, right? Now, let's actually do one. Well, let's actually prove it, okay? Let's say we already looked at these and we just looked at them and we did this by inspection, okay? If we did not have a picture, we wouldn't necessarily know. So let's pretend like we don't. So if we have just this, then how are we going to solve it? Well, we're going to take the derivative and set the derivative either equal to 0 or, we're going to take the derivative and plug in the value and see what the value is, right? Because that's all we're going to do. Find the value. It says find the value of the derivative at the extremum. So the point is 3, 2. So we're going to take the derivative. So low d high right, because we can rewrite this as 9x squared minus 27 over x cubed, right? Makes it a little easier when doing low d high minus high d low. Minus high d low all over low low. So at this point, we could just plug in 3 without simplifying anything because, well, we can, right? So this is going to be 3 cubed times 18 times 3 minus 9 times 3 squared minus 27 times 3 times 3 squared all over 3 cubed squared. So this is 27 times 3 times 18 is 54 minus 9 times 9, which is 81 minus 27 times 3 times 9 all over 27 squared. So we get out our calculator. 27 times 54 is 1458. Here we've got minus 81, well, minus 81 times 81 minus 27, which is 54 times 9 times 3, which is 27 over 27 squared, which is 729. But 54 times 27 is just 1458. So 1458 minus 1458 over 729 is 0 over 729, which is 0, right? So we just mathematically proved, not just by inspection, but proved that the derivative at 3, 2 is equal to 0. Well, here we have that the derivative of f of x equals the absolute value of x doesn't exist because we can see that the one-sided limit's different, okay? So remember, we could write this as negative x when x is less than 0 and x when x is greater than 0. This is kind of the definition of f of x. So we take the limit as x approaches 0 from the left of negative x. What do we get? Well, we're coming from the left. That's not very true, is it? Yeah, it is. So the limit from the left, which means we're talking about the negative region, negative x equals, so 0, negative is positive 0.0000. Well, the limit's just 0, right? But this is not what we're doing. Why am I doing that? Why am I doing the one-sided limits? I'm not doing the one. What I really need to be looking at is the derivatives, right? The derivative of negative x is negative 1, which means the slope of that line is negative 1. From the right, the slope is positive 1 as we approach 0. So that shows us that the derivatives are different from both sides, which means that the limit, as x approaches that value, we're coming to the limit exists, but the derivative does not. So sine x, the derivative is cosine x, and that point was at pi over 2 and 3 pi over 2. So f prime of pi over 2, which is cosine of pi over 2, which is 0, and f prime of 3 pi over 2 equals cosine of 3 pi over 2, which is also 0. So we've just proved that the gradual curve ones are 0, but the peak one is negative, or does not exist because it's not differentiable at that point. Now, example 1, we showed that each relative extrema, the derivative is either 0 or doesn't exist, right? So the x values at these points are what we call critical numbers. So either it doesn't exist at that value or we have horizontal tangency. Either way, C is considered a critical number. So we're going to define a critical number real quick. As long as the function is defined at C, okay, this is really important line. If the derivative is equal to 0 or if it's not differentiable at that point, then that is a critical number. But like I said, the critical number has to be in the domain of f. Doesn't have to be in the derivative, but it does have to be in the function itself. So if f has a relative minimum or maximum at x equals c, then x equals c has to be a critical number. This does not necessarily go the other way. Just because it's a critical number does not mean that it is a relative maximum or minimum. The only thing that's guaranteed is that if we have a maximum or a minimum, it has to occur at a critical number. So if you have any questions about relative extrema, please shoot me a remind or ask a question in class.